cover bosonic open, tree-level bosonic open string and bosonic closed string. Let me just try to tell a few words why string perturbation theory is relevant or important at this time. We are doing research in string theory for probably almost more than 50 years, but it's still not clear what is the structure of this theory. And up to this point, there are two concrete things that has helped us to understand string theory. And one of them is string perturbation theory, and another thing is the rich non-perturbative dualities. So though string perturbation theory is a pretty well understood subject, but it's still interesting, and I feel it will help us to learn many things about string theory. We still need the techniques of string perturbation theory. And second reason is that in last 3 or 4 years, there has been a revived interest in string perturbation theory, because people have understood that there are small things in string perturbation theory is yet to be clarified, and various people are working on that. It started from a paper by Ed Witten, and then various paper by Ashok Sen and Roji and other people. So that's why I feel that string perturbation theory is still a very interesting subject. And let me say that, so what is string perturbation theory? What do we mean by string perturbation theory? I think I can assume that everyone in this audience knows about quantum field theory. So string perturbation theory is a Feynman diagram-like expansion, perturbative expansion in string theory. Okay, so can you see it? So as I said, it's a Feynman diagram like expansion in string theory. Okay, so let me just say what we mean by that. So for example, if I take an example of lambda phi 4 theory, let me take QED, lambda phi 4. So the very basic scattering in QED is the scattering of 2 electrons by an exchange of a photon. So you can think like it's this is basically motion of 2 particles where they are interacting at various points, and you can usually this is so you can also think of it as a sum over world lines. Okay, usually that's not the way people follow in first course in quantum field theory, but you can think of it as a propagation of particles which and you can sum over all the world lines in space-time. And similarly, the scattering in string theory is the very basic scattering in closed string theories. For example, it's like, so this is the direction of time. 2 strings coming, joining and forming another string, and then splitting into 2 more strings. So this is a 2 to 2 scattering. This is a pictorial diagram of 2 to 2 scattering in string theory. Okay. So the way we compute string scattering in string theory is that there is so we basically, string scattering is sum over world sheets. Okay, and we will be a bit more precise about what we really mean by sum over world sheets. But this is basically the idea, and the perturbative expansion is something like that. So this is the zeroth order perturbation. The first order perturbation is and you can go on like that. So this is the idea of string perturbative expansion. So let me now tell you the purpose of these lectures, that what I'm planning to cover. It's a big subject, so I can't really cover, I can't teach a whole of string perturbation theory in 4 lectures. So, if in my mind, there are mainly three aspects of string perturbation theory. They're not really disjoint, they're related to each other, but mainly there are 3 aspects of string perturbation theory. Maybe there are more, but as per my knowledge, there are 3 aspects of string perturbation theory. One is the structural aspect, formalism. What I mean by that is, for example, in quantum field theory, we prove unitarity, we compute mass renormalization, we compute multi-loop diagrams, and we know what is the how to do that, the LSZ prescription and everything. So, and in string theory, we also need to know these things. So let me just write it like that: unitarity, mass renormalization, etc. The second aspect is, basically, this is another interesting aspect, is that even if we assume that we know everything about the structural aspects of the formalism, there's still the question of computing, doing explicit computation of multi-loop amplitudes. And this is not a very straightforward exercise. For example, people have, I think up to 1 loop, it's not that much difficult, but beyond 1 loop, 2 loop or higher, there are still research, means we don't yet know the full understanding of 3 loop superstring amplitude yet. We know and we know in 2 loop, we just know 2 loop 4-point function, and there are some results of 2 loop 5-point function. So this is another thing that people are working nowadays. And third aspect is really the aspects of, so once you know these expressions, then there are various things you can ask. Is that you can ask this question of poles and branch cuts, and what is the ultraviolet behavior, how they depend on dimension. But as I said at the beginning, that there is another building block, another way to understand string theory is the wave of non-perturbative dualities. And in last 10 or 15 years, there has been some progress in understanding the low energy limit of string perturbation theory and its interplay with duality symmetries. As I said, that these are not really disjoint things. You basically, they are tied together. But if you, for example, open a paper, probably new paper in archive, you can broadly classify them in these 3 categories probably. So I will try to say something in all these 3 aspects, maybe more on A and C, not much in B. So with this thing in our mind, let's just start from probably everyone knows it, but let me just review it. So let's review the bosonic string theory. In flat spacetime. And let me also mention that I think we can safely say that we don't know much about string theory in non-flat spacetimes like ADS or other kind of spacetimes. We mostly know about string theory in flat spacetime or flat spacetimes, orbifolds or Calabi or manifolds. But the full moduli space of string theory, the full set of means the full understanding of string theory in all possible vectors is an unsolved problem, and it's still a very challenging, important problem in string theory. So I don't have anything to say about that. I will just mostly talk about string theory in flat spacetime. What is the action? So string theory is based on, so usually when we do quantum field theory, we write down a quantum field, we quantize it, and we represent then we find that the oscillators satisfy some commutation or anti-commutation relation. And then we interpret them as this particle creation or annihilation operator, and that's the way we do quantum field theory. In other words, we do quantum field theory in terms of first having a quantum field and then quantizing it. And in that formalism, it's very natural, the particle number is not conserved. And the framework of quantum field theory is very natural to incorporate that. But in string theory, one can imagine, one can do string theory in principle using string field theory, where you will have a string field, you will quantize it, and the oscillators of string field will represent strings. And there has, in old times, people have understood some structures of it, string field theory, and in recent time, people have started working on it again, superstring field theory, by mainly like researched by Ashok Sen and collaborators. So, but what I will focus here is basically string perturbation theory, which is mostly based on a world sheet approach, which you can think as a first quantized formalism, where you put the interactions in certain sense, well, in particle physics at least, if you do particles in first quantized formalism, you put the interactions by hand. And that's the way you incorporate non-conservation of particle number by putting certain things in by hand. In string theory, as we'll see that interaction, there is not much concept of interaction point. I will try to clarify this more today. But this is a formalism, what I will talk about is basically first quantized formalism, which is based on the world sheet approach. Rather, it's not the approach where you will have a string field and you quantize and you will get strings out of it. Maybe at the end I will try to say something about how these two formalisms are related, and you will see that many of the structures are closely related in string field theory and string perturbation theory. And for certain things, string perturbation theory is probably easier, and for certain aspects, mainly for the structural aspects, string field theory is more useful. But I'll try to say something about that at the end, but at this moment I will just talk about string perturbation theory. So the action is based on, the string perturbation theory is based on an action written down on the world sheet, which describes the propagation of string in space-time. So the action is okay, so this is the space-time coordinates x mu. Which are just world sheet which are just vector fields on the they are they're scalars. They're scalars on the worldsheet. Scalars on the worldsheet. With SO d minus 1, 1 flavor symmetry. Okay, and when I write here H is the Ricci curvature. So okay, this is the metric on the worldsheet. This is the metric of space-time. And this is the Ricci scalar. Ricci scalar on the worldsheet. And this is the scalar field in the space-time. So you can think of it as a scalar matter coupled to gravity on the worldsheet. On 2 dimensions, the gravity is not dynamical, so you can integrate this out to get the Euler characteristics. You will understand the importance of this later. I will say something more about this later, why I wrote this term. So the dynamical degrees of freedom are these worldsheet scalar fields, which are vectors in the space-time. Okay, and so I will not go through the details. I will just I'm just trying to review this. So there is a large. This symmetry has this action has a large group of symmetries. So firstly, there is a Flavor symmetry, so d minus 1, 1, and there is a then the main 2 things that I will use is basically there is a so this is so let me draw a diagram. Let me denote it as a sigma. So this is the action on sigma. So there are symmetries which are diffeomorphisms of sigma, and by diffeomorphism of sigma I mean the diffeomorphism of the space-time worldsheet metric. And also there is Weil symmetry, Weil rescaling symmetry, where you can scale the metric to a local conformal factor times the original metric, and you can easily put that back in the action, and you can see this is a symmetry. So these are gauge symmetries on the worldsheet. And in order to quantize them, you need BRST. There are many ways to quantize them actually. You can go to light cone gauge, but light cone gauge is not very useful for multi-loop amplitudes. So we will use the BRST quantization. Okay, and so in BRST quantization you introduced 2 ghosts, BC, and you have a BRST operator Q, which is in this case only nilpotent. Q square is only 0 when D is 26. Okay, so if you do this computation, you will find that the q square is nilpotent is when d is equal to 26. So this quantum theory is only consistent only in 26 dimensions. Okay, so if you do though I am saying in this way, this is the modern understanding of string theory, but historically when people discovered, the first thing people discovered is an amplitude. They didn't know anything about the action, anything about BRST symmetry, what is the underlying theory. They wrote down an amplitude and they were trying to understand the properties of the amplitude. And at that point there was, and when the amplitude was written down, it was written down by Veneziano in 68. And when he had written down the amplitude, he had written down the amplitude in 4 dimensions. So he was not thinking about extra dimension, but then later people computed loop amplitudes, and only then they understood that the loop amplitude has nice properties. Mainly the open string loop amplitude is unitary only in 26 dimension, and the closed string amplitude firstly is unitary only in 26 dimension, and secondly it's modular invariance in 26 dimension. So these were the two, historically these were the crucial hints to understand, to go beyond 4 dimension and to think about this theory in some large space-time dimension. This is I'm just telling you the historical perspective, but yeah, if you do the BRST quantization and if you demand that the BRST charge is nilpotent, you will find that this is in 26 dimension. D is equal to 26. And then, so let me, yeah, the two.
Beyond that, what tree level tells you D is less than or equal to 20.
Yes.
One loop tells you D is equal to 20.
Yes, and also in tree level, I think if you demand that the second set of oscillators to decouple, that also gives you D equals to 26. Yes, but I'm saying that if you write down the amplitude, you will say that especially for open strings, and again means it hits you on the face that amplitude is not unitary. In tree level, when people understood the oscillator.
Even in tree level, the amplitudes fail to be unitary in
greater than 26 dimensions. Yes.
Questions are not positive.
Not positive, yes. So let me now, well, I'm trying to tell 5 lectures in one lecture, but that's my point. I should. Okay, I'll try to do that. Okay. So when you quantize this action, you get the spectrum, and there are various states. But I will just say some of only a few states. So the states in string theory have mass. Open string theory have mass this when n is an integer, positive integer, non-negative integer. And the states you can draw in this graph where I'm plotting the spin here and mass here, and these are called rigid trajectories. Okay. And for this, for example, for this rigid trajectory, the states follow this relation: J is equal to alpha prime m square plus 1. Okay. Anyway, so this is the spectrum. You will, if you quantize open string theory, you can see the spectrum. You can compute it, all the states. And now let me write down the gauge fixed action. At this point I am using complex coordinates on the worldsheet. These are the complex, I am using the same later, that's confusing. But at this point I am choosing a very particular basis for the metrics, which is the metric is locally and let me complete the action first. And I have chosen a particular basis for the metric. Okay. So now let me. I haven't really explained anything, and I'm still not explaining. And I'm just telling you the dictionaries because. Yeah, it will take some lectures to explain these things, and probably all of you, many of you know this. I'm just trying to set the stage for the discussions. So then the question is that how do you compute amplitudes in string theory? And an important thing in this, in order to compute amplitude, is called the operator state correspondence. So let's consider 4-point function. Again, let's draw the diagram. And the point is that you can map it using these two symmetries I mentioned here. You can map it to a sphere with 4 pans. Not pans, 4 cylinders attached to it. And so if I take a cylinder, semi-infinite cylinder, probably this is also everyone knows about this, but let me just try to explain this point. That if you take a semi-infinite cylinder, let the metric on the cylinder is dS square is equal to du square plus d theta square, where u is this coordinate and theta is this coordinate. And wait. Yeah, and then you do a coordinate. Sorry, I think I did the other way around. Yeah, this is fine. So then you define u is equal to log r. Okay, and the point is that you can map this semi-infinite cylinder locally around this in this local neighborhood. You can map it to a, so let's this be a complex plane, and you can map it locally to a disk with a point removed. Okay, so if you do this transformation, then the metric becomes ds square becomes 1 over r square dr square plus r square d theta square. And this is the metric on complex plane with this conformal scaling factor 1 over r square. but the system, the Lagrangian we have, while symmetry is a symmetry, so you can locally rescale things. So if you remove this point, then the neighborhood of this point can be mapped to a semi-infinite cylinder. And this is the basic idea of operator states correspondence, which basically means that you can map this state at infinity to a point, to a local operator inserted at this point. Okay, and we will use it. This is one of the things we will use always. And this is not always true. This is only true. This is true in this conformal field theory. And so the goal will be. So let me now write the rules. Okay. Rules for computing amplitudes. So the first thing is that you have to find, once you are convinced by this that you can map a state in infinity to a local vertex operators, then you have to find appropriate vertex operators. And these vertex operators, if we want to compute S matrix element, these vertex operators vertex operators should be BRST invariant. And let me also state this. I'm not showing this. That this condition implies that firstly that these vertex operators will have conformal dimension 1, and amongst many other things it also implies this on-shell condition on the spacetime. It imposes the on-shell condition on the spacetime, and it also imposes the gauge condition on the spacetime, the transverse, that when you have gauge bosons, that the polarization should be transverse. This also comes from this BRST condition. Secondly, is the first. The second thing you have to do is that you have to decide that what do you want to compute, whether you want to compute a 3-level amplitude or a 1-loop amplitude or a 2-loop amplitude, and you have to find the appropriate worldsheet for that. Okay, so which means that if you want to compute a 3-level amplitude, you have to choose sphere, and you have to insert the vertex operators. This is a choice. This is I probably should write choose. And the third thing is that you have to insert the vertex operators now on the worldsheet, and you have to compute the operator product expansion. Okay. So insert the vertex operators. And compute OPE. Okay, and today I will mostly discuss 3-level amplitudes, so let me just write down the OPs I will use. Means you can derive this, but I'm not I'm just stating things, so. This is actually in open string theory. Okay, and okay, you will find that we will use it. And then there is another step. We have to integrate over the positions of the vertex operator. Actually, there is another step. You have to integrate over the moduli of the surface. But today I will only focus on tree-level amplitude. So let me just stop here. We will come back to the fifth point later. And there is, when I say integrate over the positions, I will explain it now. You don't need to integrate over all the position of all the vertex operators. So let me come back to this part. Probably everyone has done this computation, but just let me do it again just to illustrate the point. Let's consider open bosonic string. And consider the simplest thing you can compute, simplest amplitude you can compute is 3 tachyon amplitude. Okay. So as I said, the tachyons in open string theory has mass -1 over alpha prime. And then the first step is to find the appropriate vertex operators. The vertex operator for tachyons is and then the next point was to choose the appropriate wall sheet. We want to compute the tree level amplitude. So the tree level amplitude is you can think of it either as a disk where you insert the 3 vertex operators on the boundary, or you can map it to half plane and you insert the vertex operators on the real line. Okay. And now, as I said, that I'll clarify on the fourth point that on a plane you have a symmetry, SL2C symmetry, where Z goes to AZ plus B over CZ plus D. And AD minus BC is 1. Okay, so there are three parameters, 3 complex parameters. But here in this case, you want to keep the boundary fixed, which means this SL2C will reduce to SL2R, which means A, B, C, D are real now, satisfying the same condition. And if you want to fix this redundancy, then you have to fix some of the points. In other words, using this redundancy, you can fix 3 of the vertex operators because there are 3 parameters. You can fix 3 of the parameters on wherever you want. Okay, and that's the way to fix the redundancy. And this is true for any also higher point function, that whenever you want to compute an endpoint function, you really have to integrate over n minus 3 points, because 3 points you can fix on any point on the real line. And this can be, so this is a way you can do the computation, and you can compute the Jacobian to fix these points on these 3 particular points, say y1, y2, y3. We will not integrate over them. Alternatively, there is another way in terms of the BC ghost system, is that you will find that the BC ghost system, the C ghost, has 3 zero modes. And since the C ghost has 3 zero modes, you have to soak up the zero modes because they are fermionic. And if you do not soak up the zero modes, the amplitude becomes, the amplitude becomes 0. Is it true? It should become infinite. No, it becomes 0, yes. So, in other words, whenever you want to compute an endpoint function, let me just illustrate that point. You have to soak up the 3 zero modes, which basically we insert 3 vertex operators with a C0 mode. And rest of them you have to integrate over their positions 4 to n. Okay, and I have to be bit more specific about what is the domain of integration, but let me just, yes. Oh, sorry. Okay, so this is the general. So this is the expression. I'm not very careful about the normalizations. These normalizations are very important if you want to extract some. In particular, if you want to do these things, or extracting low energy expansion and comparing it with S duality, these numbers are very, very important. But I'm not careful here. But if you want to know the numbers, I can show you. I can show you at some point. Then let's compute the three tachyon amplitude. The 3 tachyon amplitude when you take the OP of the 3 C0 modes. So there are 3 C's, and you use this OP expansion to get for 3-point function. And then you have to take the OP of these exponential factors, which you can do those using those standard OP relations, and you will find that it is 2 alpha prime times k1 dot k2 log y12 plus 2 other terms. And then if you use what is k1 dot k2 using the on-chain relation, you can easily find that it ultimately turns out to be y1, y1, 2, y23, y31 over y12, y23, y31, which is basically 1. And there will be, as I said, there will be coupling constants here and normalization. So this will basically give a factor of coupling constant, nothing else. So what is this? So this is a very simple computation. But now you can ask that what we have learned from after doing this computation. The first thing you learned is that the 3-point function of the scalar fields, right? That's the computation we did. So if you want to write down an effective field theory for the tachyons, if you want to write down an effective field theory for the tachyons, then the effective field theory will have a term lambda phi q, right? Where lambda is this coefficient. I must not some lambda here. Okay, so if you want to write down an effective field theory, then the way to do that is to compute the amplitude, extract the 3-point functions and higher point functions, and to write down the low energy field theories. And sometimes this is a way to get the low energy field theory data out of it. And let me illustrate this by one more example, which is a bit more involved. We have to do we have to compute more. So let's compute the 3-point function of 3-point function of photons in open bosonic string theory. Okay, so you want to compute. You can also compute 2 tachyon 1 photon, 1 tachyon 2 photon. But let me just do this. Okay, and before I do that, let me also say one more thing which probably everybody knows, is that there is a way to incorporate gauge symmetry in open bosonic string theory. And the way to do so, what is the first? Let me write down the vertex operators for photons. The vertex operators are okay. Now this is the vertex operator for photon, but if you want to vertex operators for non-abelian gauge bosons, then the way to do that is basically introduce another factor which is called a Chern pattern factor. This is some matrix, some adjoint matrix which is written in the fundamental representation. Okay, so if you want to consider SU2 gauge group, if you want to consider SU2 photon, then this will be the sigma matrix written in the fundamental representation. Okay, and historically the pictorial picture was that you can think open strings as, this is a picture of an open string, and you can think the endpoints as 2 quarks, and one endpoint is transforming in some fundamental representation, and the other endpoint is transforming in the either complex conjugate or the same representation, depending on whether it's an oriented string or not. And that's the way you can get this T matrices. Okay, this is historically this is the way people introduce gauge symmetry in open string theory. And based on the nature, I'm not explaining this, I'm just stating the fact. Based on the nature of these amplitudes and their factorization property, you can argue that this can only belong to 3 categories, either SU or SP or SO. In other words, you cannot have exceptional gauge groups in open string theories. You can argue it just by looking at the relations, it has to satisfy at the polarization. Later people understood SU or SO in terms of D-branes and orientifold planes. And does SP have some, sorry? Orientifold planes. Yeah, I didn't. Okay. So you can also get, later people understood in terms of D-branes, but this was discovered long before that. And one conclusion was that you cannot get E8 out of it, exceptional gauge group out of it. And why E8 is as you know that E8 is important for. So there is, if you consider string theory in 10 dimension, there are certain anomalies, gauge or gravitational anomalies, which only cancels for SO32 or E8. SO32 was realized in open string theory, but for some time it was a confusion that how we can get E8 from string theory. But it was clear at that point that you cannot get E8 from open string theory. So okay, these are the vertex operators, and we want to compute the 3-point function again. So we insert 3 vertex operators here. and the OP we want to compute. So again, to compute the amplitude, we have to put 1 factors of C with each vertex operator, since there are only three vertex operators. And so the OP of the C is very straightforward, is same as here. Let me just do this part. Okay, so let me just do the OP expansion. I will not do all the steps, but let me do first few steps. Let me not write the group theory factor now. So this is the OP, this is the OP we have to do. It's a very easy thing to do. So the exponentials will contract with each other. Now we have to figure out how the dels, what are the ways to OP? The OP can happen is that when this delta x, take OP with this delta x, or you take delta x with an exponential factor, okay? And to consider all possible OPs. That's that we have to do. So let me first choose a very particular pattern. And the pattern is that we will choose to, we will take the OP of 2 del x's, and then the third del x, we have to contract it with some exponential factor. There is no other way. Okay? So this is one pattern, and the second pattern is that all the del x contract with exponentials. They do not contract amongst themselves. These are 2 different patterns. So let me first do the first kind, where 2 del x contract with each other, and the third one contracts with an exponential. And that's easy. So I chose to contract del mu1 with del mu2. So del mu3 will either hit this one or this one. And that will give k1 power mu3 y 31 plus k2 power mu3, k2 index mu3 3, 2, and then you will have the other 2 permutations, okay? So 2 more terms. Again, if you want to see the explicit computation, I have it, I can show you. But let me just show the pattern of this. And the third, then the other pattern is basically when the del x will hit the exponentials, and they will have k2 power mu1 y12 plus 3 power mu1 y13 k1 power mu2 y21 plus okay, so this is all the OPs if you do this and there will be the exponential factors. Sorry. ki dot kj log yi, right? Now, since these are physical on-shell states, they all satisfy. So firstly, k1 plus k2 plus k3 equals to 0, and secondly, k1i contracted with the polarization tensor is 0. These are the on-shell conditions. Okay, and using this on-shell condition, you can simplify these factors. So you can write k2 as minus k1 plus k3, but k3 hitting the polarization of the third will give you 0, so you will only get k1. So you will get k1 mu1 over y31 minus k1 mu1 over minus k1 mu1 over y32. Okay, and this is the way to simplify this. You can simplify this. You can simplify this in this way also, that you replace k3 by k1 minus k1 plus k minus k1 minus k2. Minus k1 hitting, this will contract with the first polarization, that will again give 0. So this will become just k2 mu1 y12 minus k2 mu1 y13. And in that way you can do the computations. I am not doing it here. And the end answer you will get is this thing. You get plus okay, so this is the full 3-point function contracted with the polarization tensors. And also the color factor. Okay. Now this term gives you the Yang-Mills 3-point function. Okay. So this term, if you consider ordinary Yang-Mills gauge theory, then 3 gluon amplitude is reproduced by this term plus the 2 cyclic permutations times this color factor and everything. So then the 3 gauge boson amplitude, the first point of the 3 gauge boson amplitude, the first line of the 3 gauge boson amplitude, the first line is basically coming from the known term, the Yang-Mills term, but there is a higher derivative term, right? What do I mean by higher derivative term? Here you have only one derivative, here you have 3 derivatives. Okay? And if you want to write down this 3 derivative term, this 3 derivative term comes from an f cube term. Okay, so this is 2 order alpha prime times trace f cube. This is some number times alpha prime. I haven't, again I can show you, I have done these computations, but in order to get from this step to this step, you have to be very careful with the symmetry factors and everything. So this will be just some number times order alpha prime. I can't tell you right now, but this is order alpha prime times trace f cube. So if you compute 3 gauge bosons amplitude in open bosonic string theory, you get ordinary 3-point function, but there is a high derivative correction. At the level of 3-point function, there is a high derivative correction in open bosonic 3-point function in the Yang-Mills, the low energy Yang-Mills theory. And when I first studied it, I thought, why it's a big deal? Okay, it's some high derivative. But in recent times, so firstly, these derivative corrections are important to understand the 4-point function and other structures, which I didn't know at that point. I'll try to tell more about that. And secondly, recently we have seen this new approach to demand uniqueness of string theory from various approaches. And one approach was adopted by Kamino, Edelstein, Maldacena, Zubedov, and they looked at the higher derivative corrections to the Graviton 3-point function. And in that way, they basically argued that whenever you have a high derivative correction, then you have a causality violation, and the causality violation can only be restored in this context of in the context of string theory. You cannot have just Einstein gravity with high derivative corrections. But and this is
only the strong word.
Sorry.
Only the strong word. One of the examples. Can you only restore in string theory? I think it's too strong.
No. The string theory gives an example, yes. But the argument was that you need massive higher spin particles. Yes, the infinite tower of massive higher spin particles. Yes, and sorry.
Only known.
Yeah, this gives an explicit, consistent example of the thing Maldacena and collaborators are considering. So. So that's why these corrections, and these are corrections in open string theory, in bosonic string theory, as far as I know, that there is not much. So in the context of superstring theory, these are important for other reasons. You will see that in the context of duality symmetries, these higher derivative corrections plays very important role to understand the duality symmetries, how duality symmetries act, and how do you know, because non-perturbative duality symmetry relates perturbative expansion to it relates a weakly coupled phase of a string theory to a strongly coupled phase, and to check its duality, the only thing you can trust is basically the things that are not renormalized, and in the context of n equals 1 superstring theories, there are higher derivative corrections to n equals 1 theories. At the level of 3-point function. So if you consider n equals 2 string theories in 10 dimension, they do not have any high derivative correction at the level of 3-point function, but n equals 1 string theories do have corrections at the level of 3-point function, and they just get single contribution in the perturbative expansion. And this is a very interesting thing. So let me just I will probably give you the computation. Sorry.
Del square f cubed and higher up.
Yes.
And that should be captured. Some of the terms they will also be coming from this 3-point function.
Del square f square. Del square f cube. So I think there is no del square f cube correction so at the level of 3-point function, when you have del square, I think that's killed by Mandelstam.
Del square, I mean, put it somewhere inside.
Okay. The only thing I can tell you is that all the known examples, there is no, at the level of 3-point function, there is no correction, del square correction to 3-point function. For example, if you consider heterotic string theory, let me just tell you the example, I'll come back to that. This is a very I find it interesting, this may not be interesting to everybody. So in heterotic string theory, at the level of 3-point function, there are corrections, okay? There are corrections, I should have been more precise. At this point I was considering Young-Mills. Just to tell you the example, let me switch it to gravity, and at the level of 3-point function of 3 gravitons in heterotic string theory, there is the usual Einstein-Hilbert term plus there is a R² term, okay? And the point is that both of them come from tree level in heterotic string theory. When you consider duality, okay, probably I'm just telling too many words, so if you don't understand, just ask me. So both of them are tree level, and if you consider the action of S duality on these terms, you will find that this R term, the Einstein-Hilbert term, goes to a tree level term in open string theory. But this tree level R squared term goes to a two loop term in open string theory. Okay, so there is no, so this is a miraculous, not miraculous. This is something very interesting that doesn't happen in n equals 2. That you take a tree level term here, which comes from sphere with 3 vertex operators, and that goes to an amplitude where you have to, which is a two loop amplitude, order G1. So in heterotic side, this is GHO square, and this goes to a term of order G1 in type 1 theory. Okay, and this has interesting consequences. Let me think. I think I confused two things. Sorry. This is, I'm discussing 3-point function. This starts with 1 over GHO square, and this goes to 1 over G in type 1 string theory. So in one side you have 3 vertex operators on sphere. On other side you have disk with 3 graviton vertex operator plus disk with a cross cap with 3 vertex operators. Okay. So that's why these higher derivative corrections play a very important role in understanding duality. I'm not telling anything now for bosonic string theory because there's no, usually these duality arguments heavily rely on supersymmetric non-normalization theorems. So I'll try to tell about them when I discuss superstring theory. But that's the importance of, that's one reason to study higher derivative corrections. Okay. Let me now just briefly mention the 4-point function, and then I'll try to say something more general about the amplitudes. Lambda mu
Del mu r whole square. Why that should not exist?
Lambda mu del mu r.
Del mu r whole square.
Okay. I think whenever you have del, you will see that at the case of massless things, it will involve a Mandelstam variable, and the Mandelstam variable at the level.
That's what you're saying. I mean, those may exist, but then those
at the on-shell level, you cannot see
they
that.
can be field defined.
Yeah, on-shell level, you cannot have derivative in 3 point.
Did the scattering amplitude calculation in some non-trivial background, then those might exist.
Yes. In flat space-time, they don't exist. In other words, they're ambiguous. You can always generate it from field redefinition, but I don't think there is a non-ambiguous term. For tachyon amplitude, I will not go through the derivation. It's given in many books, and in some sense, string theory started from this amplitude. Veneziano wrote down this amplitude to explain some experimental data, and then people tried to understand that what is the underlying physics for this amplitude. So let me just write down the amplitude. So the Veneziano amplitude for 4 tachyons is Okay, so this is the amplitude. I'm not giving you the derivation, but let me just try to tell you some properties, and many of these properties remain true for other amplitudes in open string theory and closed string theory. And these amplitudes are, these properties are very, they were, when people wrote down this amplitude, they were interesting for some experimental reasons. And now there is a renewed interest in that because of that reason that there was a recent paper 2 weeks back probably, where they are basically assuming some of these properties and then trying to argue that the nature of these amplitudes are universal in certain regimes in the parameter space. Okay, so that's why I'm just writing down the properties which is true for Venezian amplitude. And now the goal is, one of the reasons, one of the things that people are now looking at is that how many of these things you can just assume by hand and argue that this is the amplitude which is consistent with the principles of physics, and probably in some particular parameter space. They did it for, this recent paper did it for large S and large T, both of them are positive, which is a imaginary angle scattering, but they can prove that this is universal. Venezian amplitude is universal. So that's why I'm writing down all these properties. So the first. Yeah. I will also try to say what are the things they assumed, but I'm writing down because some other people can assume some other set of things and can argue probably for some other regime. So firstly, there are poles. Poles of the amplitudes are when alpha of S, which is alpha prime S plus 1, is non-zero integer. Okay, is either positive or zero, positive integer or zero. N is positive integer or zero. Similarly, there are poles also in T channel. Note that the same amplitude contains infinite set of poles, both in S channel and T channel, but they do not contain poles. There is never a simultaneous pole in S channel or T channel, right? So this is an amplitude where you can either expand it in S channel, then all the residues are some function of T, and there is an infinite number of poles. And there is also, you can expand it in T channel, again you will have infinite number of poles, and all the residues will be a function of S. So this property in old days, people still call it the same thing. This is called duality. This is another one duality of the amplitude. Okay, where basically S and T is T, and means function of ST same as T and S. And this is one thing these people assumed. They assumed duality of they assumed that the amplitude is has this property, and they proved that this is a very strong constraint on the amplitude. Okay. Now, so this is one property. Secondly, you can argue that whenever alpha prime S plus alpha prime T is integer or zero, the amplitude is zero. So the amplitude also has infinite number of zeros. There is one other interesting thing which was emphasized in this recent paper is that there is always exactly one zero between two poles in S channel or T channel. If you expand the amplitude in S channel or T channel, then between any two poles, there is always a zero of the amplitude. And for some certain value of the choice of parameter space, there is sometimes zeros are exactly sit on the pole, and in that case, this amplitude vanishes. Okay. This is the point that was proven by these people in this recent paper by understanding the unitarity and the duality. So they didn't assume this point, but they proved this point. Third is that if you have alpha prime S, alpha of S and alpha of T large, okay, such that S over T is finite. This is known as the high energy fixed cycle scattering. And you will find that the amplitude in that regime goes like alpha prime S log S, alpha of S log alpha of S plus alpha of T log alpha of T minus alpha of S plus T times log of alpha S plus alpha T. Okay. Note one thing, that at very large energy, very large value of S and T, this amplitude dies off exponentially. Okay, so this is extremely soft in high energy regime, and usually this happens because of the existence of extended objects. So there's a paper by Susskind, Klebanov and people, where they basically showed that whenever you have extended object, then the quantization of those objects at large energy always gives you this behavior. So this behavior basically says that you have extended objects in your theory. And this is important for another reason, is that when you go on and compute the loop amplitudes, you will find that the loop amplitudes in string theory are ultraviolet finite. There is no ultraviolet divergence. And this can be, well, in my understanding, this point hasn't been completely understood, but one hint of that is basically that the vertex operators are exponentially small in ultraviolet regime, and that's a signature that probably the amplitudes are ultraviolet finite. But as I'm saying that, at least in my understanding, there's not a very clear proof or clear connection people have shown between these two statements, but this is a hint that the amplitudes are ultraviolet finite. And I will try to say something more later, but in a recent paper by Ashok Sen and Roji, they showed that this nature of the amplitude basically, though this is a nice property of the amplitude, this basically prohibits you to analytically continue the amplitudes in Euclidean space. Sorry.
What is wrong with the usual explanation that is given, at least in the one loop case, that you excise the origin by being in the fundamental domain, and the result of which in the string of parameterization, where
yes,
when you take the t going to 0 limit, where the ultraviolet divergence is actually originating from.
Yeah. No, there is nothing wrong with that. But I'm saying that gives you use certain property of the amplitude, the modular invariance, which you can argue for all loops, and you can argue that the amplitude is ultraviolet finite. I agree with that. But I'm saying that, to my mind, it doesn't give any physical picture that what is happening in the ultraviolet and how the physics is changing in the ultraviolet.
But what is wrong? The usual notion is because these are extended objects, the point there is no single point at which the intersection.
I agree with that.
What is wrong with that?
There is nothing wrong with that, but I'm saying that for example, let me say this example, that when people consider this Dirac fermion in the potential, they found a unitarity violation, and they knew because of pair production. But before you got quantum field theory, you didn't really know how to kind of deal all this situation.
But are you worried that there could be other divergences?
No. I trust all the things that people said this is ultraviolet finite, and the arguments are mathematically rigorous. But
I'm not sure. I thought the whole idea was that because you have master normalization, supposing you have to shift your vacuum or if you have to shift your mass from this thing, in that process, whether you might be, the arguments were sort of at a very qualitative level, no? That, okay, the regions of moduli space where there are no regions of moduli space from which you would get the night ultraviolet divergences.
Yeah, I think
there might be other divergences.
So the argument
which are coming, maybe. It was not a. I think what is being currently done is to show that there are no possible sources of divergences even when you make corrections for.
Those are the infrared divergences.
The infrared divergence, so the ones that are always believed to be the case are infrared divergences, but what I mean to say is that no one really had shown that in a systematic way you will not generate.
I think there is one argument. So firstly, I can't prove it, but the one argument by Witten was to, at least for the simplest case in string theory, he argued that that these amplitudes can be written down as some forms on the moduli space of super Riemann surfaces, and then based on the there is some very particular form like Mumford form, and based on the nature of analytic property of these forms, he argued that these forms do not have any singularity in the moduli space. So only singularity that can come from the non-compactness of the moduli space. And then you understand the regime where the non-compact part where these boundaries of the moduli space come in. And now we understand that these boundaries of the moduli space are all infrared singularities. I think that's basically the argument.
Yeah. Because it was not, I think, very clear that all possible boundaries might correspond to some mixed kind of.
All possible boundaries.
In a more complicated Riemann surface, all the different degenerations really do correspond to physically some infrared divergences. I think was not before Witten's work.
Yes. No. And there was this problem with this in superstring. There was this problem with the singularity within the moduli space because of the beta gamma system and things. Now we understand in terms of. So I think now, at least for the simplest case, mathematically there is some argument that there is no singularity. There is no ultraviolet like singularity. Only singularities are coming from the boundary, which are infrared singularity. And I as I said that I haven't gone through the proof completely because this depends on some forms in the moduli space, Mumford form and something, which has been proven for bosonic string for I think arbitrary loops. I think for superstring it hasn't been proven. I think it's for 2 or 3 loops they have extended. But that's okay. It's a very personal choice. I'm saying that this doesn't really tells me about the physics in the deep ultraviolet. That's what I'm saying.
The question you're asking is there's a soft behavior of the scattering algorithm.
Yes.
How is this related to how the modulus space is set up?
Yes, that's one question. Second question is that if I want to do gravitational scattering at this very, very high energy, is there an effective description I can give where I understand the softness and the ultraviolet finiteness? That cannot be a field theory, right? So in other words, what is the general property of an amplitude that makes it ultraviolet soft? And what is the most general nature of that? At least I don't understand.
So in the string field theory, there are like exponential.
Yeah. This kind of vertices. Yes.
The vertices.
Yes.
The vertex operators are surface.
Yes.
But if it clear in string field theory, why they are ultraviolet finite? The things that we calculate are ultraviolet finite.
I may be wrong, but as far as I know, the argument for finiteness in string field theory is the same argument. I am not aware of any other argument in string field theory. But yeah, people sometimes argue from this, but as I said, I don't think there is a clear statement between exponential nature and the finiteness. And this nature has, as you know, that has been very proven for very general string, means almost for all the string standard flat space string theories by Gross and Mende. That is a very general nature.
The expression suppression is a space-time theory. You're asking, how do I see ultraviolet finiteness from space-time?
Yes, precisely. Yes. Modular invariance is something that you argue at the level of wall sheet, which is I trust and I have seen in one loop, but it doesn't give me the space-time picture. One is this extended objects, which gives it log s, but
it doesn't give this ultraviolet finite.
at least not to my knowledge. Yeah, maybe some. I don't understand. Yeah, sorry. So okay, so this is one very general property. As I said, that this was first observed by I think it was there in Veneziana's original paper, and this was very general, proved for very general amplitude by Gross and Mende for closed string, and Gross and Manis for open strings. I think the open string case is more interesting when you go higher loops, but I don't fully understand that. Okay, and let me just say one more thing, that this behavior also prohibits you to continue from Euclidean signature to Lorentzian signature for the full amplitude, and that creates some problem for proving the cutting rules and proving unitarity. And in recent paper by Ashok and Roji, they have shown this in a very nice way, that how can you have Euclidean behavior in the deep down in the moduli space, and you have Lorentzian behavior at the boundary, and you can consider both the ultraviolet finiteness and the unitarity in a general in string theory, in string field theory. Okay, so let me now just say some very general thing now about the structural part. I'll point out the more established results, and then I'll point out the difficulties, and I will go on the details that how this difficulty was resolved in recent paper by Witten, not recent, like 3 years back. So let me ask this question, that okay, so firstly, when people computed string amplitudes, I think most of them computed amplitudes with external massless states, because all the stringy states are very, very massive, and yeah, we are really interested in the low energy physics, and no one has come, to my knowledge, there is not much understanding about the massive states. But for massless states, people have computed for superstring at least up to 2 loops, 3 loops. There are some results for 3 loops as well. But then you can ask that how can you prove that these amplitudes are unitary? How to prove unitarity for these amplitudes? Okay, and let me try to give the old argument for unitarity for massless external states, and then I will say some more thing, which was, as I said, it was pointed out by a recent paper by Witten, which is 1209.5461, which is this 250-page paper, the Superstring Perturbation Theory Revisited. Okay, so I'm not discussing closed string amplitudes. I'll probably say something more about closed string amplitudes, especially the Virasoro-Shapiro amplitudes and the KLT relations next time. But let me today just tell something very general, and I'll stop after this. So let us consider the Graviton vertex operator. Okay, and the Graviton vertex operator okay. Now let us consider a pure gauge state of the Graviton vertex operator at non-zero momenta, and that is one such state is given by Okay. Now you can see that you can write this vertex operator as derivative acting on okay. So this is a worldsheet derivative acting on this. So when you insert the vertex operators, let us yes, I'm using that, yes, and that will be, yeah, I'll come back to that. So let us now consider a sphere with, say, n vertices, and one of them is pure gauge vertex, which means one of the vertex is like this. Then what you can do is that you can put this and you can integrate by parts to make it make the vertex operator. So this vertex operator, when you insert on the worldsheet, it will also have a d2z. So you integrate it by parts to make it a contour integral. Okay, and then you open the contour on the other side, and you will carefully analyze things near other vertex operators. And if you carefully analyze them, you will find the contribution vanishes. Okay, and you can do it for loop amplitudes too. You can do this. For tree level, this is not a big deal, but for loop amplitude, this is a big deal in the sense that you can keep the moduli of the loop fixed, and on a fixed Riemann surface, you can integrate it by parts to argue this. Okay, so this is true for every point in the moduli space. So this is the way you prove the decoupling of pure gauge bosonic states. There is only bosonic state in bosonic string theory, but in superstring theory too, this is the way you prove the decoupling of pure gauge states in string theory in general. Now here let me illustrate one important point. Again, this is from Witten's paper. Let note that when the momentum is 0, the vertex operator is identically 0. Okay, so if you insert the vertex operator at 0 momentum, then the amplitude is 0 because you have multiplied it by a 0. In that case, this whole thing means the contribution from all of them is 0 because you have inserted a 0. And then what is this? This is basically, so okay, let me take this, and if you take this vertex operator at 0 momentum, this becomes okay, and this is identically 0, the equation of motion. Now, if you take the vertex operator, integrate it by parts, and try to take the contribution from other vertex operators, this will be obtained by taking first the OP del x mu with the other vertex operators and adding up all such contributions. Okay, since you add all such contributions, this is the momentum operator. This is a worldsheet. This is spacetime momentum operator on the worldsheet. So this condition basically implies that the sum of momenta for external states is 0. Okay, it's a very true. We expect it to be true, and there is translational invariance. But I'm telling it again and again for the following reason: is that firstly, note the important thing, and that you can do it at a fixed worldsheet. You don't need to change the moduli of the worldsheet. Secondly, this property that the vertex operator vanishes at 0 momentum is only true for massless states, and which is basically matches with our intuition that whenever there is a massless state, there is some underlying conservation law. So when you prove the decoupling of the zero momentum massive states, you will not get any such conservation law. Okay? And secondly, for the massive external states, and in superstring theory we'll see that for massless fermionic states, the proof is not that much straightforward. You can't just do it at the level of fixed world sheet, and that leads to more complexities. In particular, you will see that the fermionic symmetries, namely supergravity and supersymmetry, can spontaneously break by loop expansion in string theory. But this argument, with this argument you can prove that any bosonic symmetry, which is a true symmetry at tree level, can never spontaneously break by perturbative expansion in string theory. This is a key difference between a fermionic symmetry and a bosonic symmetry, and it basically, since I'm not giving the other proof, I will give the next day, that it basically depends on this fact that you, to prove the bosonic symmetries, massless bosonic decoupling of massless bosonic states, you can do it at the level of a fixed world sheet, and that gives you a lot of power. But for fermionic symmetry you can't do that. Okay, so that's why the fermionic symmetries and supersymmetry can spontaneously break in string loop expansion, but momentum conservation or electric charge conservation cannot spontaneously break in string loop expansion. So this is one thing, and this heavily relies on the fact that the vertex operator for the massless state at zero momentum vanishes. And now let us consider a massive state. Okay.
Something more we can say is the soft theorem.
Yeah, you can prove soft theorems also by considering a small momenta, and the argument goes basically when you have the small momenta, certain boundary of the moduli space starts dominating, and when you go to that particular boundary of the moduli space, it is basically the statement that the soft particle will be emitted from the external legs. Okay, because basically that the way it works in field theory is that some propagator becomes dominant 1 over k, where k is 0. The same thing happens here, but you can do it. But now take a massive state. Let's take the first massive state in bosonic closed string theory. Okay. Now note that if I replace this polarization by k mu1 times some this, which is a pure gauge state, which is one of the pure gauge states, you cannot no longer write it as a total derivative. You cannot no longer write it as a total derivative on the world sheet. Okay, since you cannot no longer do it as a total derivative of the world sheet, you really don't know how to prove it, because the argument I presented here doesn't work. Okay, so that's why it's a very special thing happens for massless states in bosonic string theory and massless bosonic states in superstring theory, that you can argue this decoupling of states at the level of world sheet, which you cannot do for massive external states or fermionic states. So this is the difficulty. Then you can ask that how to prove it. Okay, how to prove decoupling of states for massive external state. And the way the proof goes is basically that any external state, this is also true here, but we have basically added luxury for massless states. When you have a massive vertex operator, which is pure gauge, you can write it as some q of some another vertex operator. Okay, it is by definition a pure gauge state. Then again I am stating a fact which I am not proving, is that these vertex operators q, this operator q, you can think of it as a D operator, DRAM operator on the moduli space. Okay. Means you can prove it, not just think. Exterior derivative, yeah. And then the proof goes like this. Let me try to give you the proof, and very soon you will understand many important features. So the proof is basically we are inserting one pure gauge operator along with many physical operator. Okay. But these are physical vertex operators, which means this is equivalent to okay, and then basically the point is that this amplitude is given by, so whenever you have an amplitude, that is given by some particular form on the moduli space. Okay, and when this happens, this you can write as some exterior derivative operator x something, and you have to integrate over the full moduli space. Let me just point out that q is the exterior derivative on the moduli space in general. For massless states, this also becomes an exterior derivative operator on the world sheet. That's the added advantage you get. Okay, but in general, this is the exterior derivative on the world sheet. On the moduli space. So you have now D of a form which you have to integrate over some particular space. Now you use Stokes' theorem to basically argue that D of a form is same as, let's call it M, is same as integration of that form on the boundary of the moduli space. Okay. Since that is the case, now we have to carefully understand the boundaries of the moduli space. Okay. What is the time, by the way? I'm just going on and. Oh, okay. It's okay. Sorry. Yeah. Okay. This is the last thing I will do. Okay. So then the goal is basically to understand what is the boundary of the moduli space. Okay. I will tell it in more details because we are running out of time. But the boundaries, let me just tell this thing, that the boundary of the moduli space is basically when a closed curve in the Riemann surface, you pinch it to 0 size. So one boundary of the moduli space of this surface is you take this closed curve and you pinch it to 0 size, which is basically becomes something like okay. These are called the boundaries of the moduli space, where basically the Riemann surface divides into two components. In this case, this is a sphere times a torus. There were 1, 2, 3, 4, 5 points. Now you have 3 plus 1 points on this component and 2 plus 1 points on this component. I am writing it plus 1 because this is a new point came out of pinching. So these are the most general. So for example, let me draw another boundary of the moduli space. Another boundary of the moduli space can be something like this. 4, 5, yes. Okay. So now we have to carefully understand that how these boundaries contribute, and we have to understand that whether they are 0 or not, to argue that the pure gauge state is whether the pure gauge state is decoupled or not. Let me illustrate just for a one loop diagram. Tree level, I will try to review it again the next day, but just to make the point, let me just review it for one loop diagram. In one loop diagram, are typically one boundary can be something like this, where you have a sphere and another torus. Okay, and you can have any number of points in any of these components. You can have 2 points here, 3 points here, or something like that. Now, the point is that, again, you can argue it, I will try to show it next day, that only boundaries contribute where the momentum flowing through the node satisfies a on-shell condition, which means the momentum flowing through the node should be k square equals to m square, okay, or k square equals to 0, because in either case k square minus m square is 0. How it can happen? It can happen in two ways. If a component has one vertex operator or 0 vertex operator, right? Because if you had 2 vertex operators, then k1 plus k2 may satisfy on-shell condition, may not satisfy on-shell condition. In other words, you can analytically continue away from on-shell condition. But whenever you have a single vertex operator or no vertex operator, then exactly at 0. So there is no way to analytically continue. Okay? So the only type of boundaries that will contribute is this boundary. This boundary will not contribute. So this is the pure gauge vertex operator. So the pure gauge vertex operator can be on this side, or you can have no vertex operator on this side, or you can have one vertex operator on this side, one other vertex operator on this side, right? And we have to understand what does it mean in terms of, we have to physically understand what does it mean. Okay, so what does this mean? This is basically a tadpole diagram, right? You can think of it as some state here and it has a tadpole diagram. Okay, so in bosonic string theory it will be important because there are one loop tadpoles. But let's assume there is enough number of supersymmetry to cancel the tadpoles. So in that context you can ignore this diagram, but you have to ensure that there is enough number of supersymmetry and that is not spontaneously broken. Okay, so I'll come back to that more next day, but for the moment ignore this diagram. This diagram basically denotes a diagram when a symmetry is spontaneously broken by a loop effect. This is basically the gauge parameter is getting a vacuum expectation value at one loop level. When a vacuum expectation value gets at one loop level, that means the symmetry is spontaneously broken at one loop level. And what does this vertex operator, what does this component mean? This is a one state, external state, and you can think of it as a mass renormalization diagram, right? So if you insert the same state here and the shadow state here, then this is basically a mass renormalization diagram, and this is the 5-point function of that same state at the level of sphere, right? So then there are two contexts. There are actually three. We ignored one. There are two contexts where a symmetry can spontaneously break, or the pure gauge states don't decouple. One is that when the symmetry spontaneously break due to a loop effect. Secondly, the external states you are considering have one loop mass renormalization. Okay. So then, now have I managed to convince you that how the decoupling of the massive states is different from the decoupling of the pure gauge massless states? Because all these subtleties, carefully analyzing the boundary, mass renormalization, understanding things at the boundary of the moduli space doesn't matter for massless bosonic states. Okay, they only matter for massive bosonic state. Massive bosonic state we will see later for massless fermionic states, which essentially means that the massive gauge symmetries associated with this state can be spontaneously broken or can get loop corrections, okay, because that may happen that it spontaneously breaks and there is a nearby vacuum where it's exact symmetry. Or there are some external, the massless state suffers from mass renormalization, and in this case also the pure gauge states don't decouple, okay. So that was the status of the thing when Witten wrote this paper. But then, so this is still the genuine, the loop, the symmetry can always spontaneously break due to loop effect. But then later, Ashok Sen and collaborators basically argued that this effect happens because you are not considering you are not doing LSZ prescription properly for the external states. So that the external states you are putting satisfy tree level on-shell condition, but when you have quantum effects and when there is mass renormalization, then you have to consider the mass renormalization and put appropriate LSZ condition before doing the loop computations. And if you do that, you can argue that this also doesn't matter. So the only thing remains is this. So that's basically the difference between the gauge invariance of a massless state and the gauge invariance of a massive state. Have I managed to convince this point? I think that's the new thing that happened in last 3 years. All the things I said is 30 years old. Okay, let me stop here today.